The sun is blazing hot. So why is space still freezing cold? The answer is far stranger than it sounds. If you enjoy watching these type of videos, subscribe to the channel. Let's begin. Your intuition says that if the sun is extremely hot, then the space around Earth should also be hot. On Earth, that sounds reasonable. If you stand near something hot, you usually feel that heat around you. But space does not behave like Earth, and that is where the confusion starts. You hear that the sun's surface is around 5,500 degrees Celsius, about 9,930 degrees Fahrenheit, and that Earth is only about 149.6 million kilometers, or 93 million miles, away. That sounds close enough for the whole area to be extremely hot. So your brain takes a rule from normal life and applies it automatically. Hot source nearby means hot surroundings. But that rule depends on something Earth has and space mostly does not have: a lot of matter between you and the heat source. That is the first thing you have to reset. On Earth, most of your daily experience with heat happens inside air. Air is everywhere around you. It touches your skin, it moves, it carries energy. If a room gets warm, that warmth spreads because air molecules collide with each other and move around. If you touch a hot object, energy moves into your hand through direct contact. Those are normal Earth conditions. Space is not like that. Space is not a room with very thin cold air. It is a near vacuum, which means there is almost nothing there compared to Earth. So the next question is, what are you actually calling heat? That matters because people often treat heat like it is a kind of substance that floats through emptiness. It is not. Heat is energy being transferred from one place to another, and that transfer can happen in different ways. On Earth, the most familiar ones are conduction and convection. Conduction is direct contact. A hot pan burns your skin because atoms in the pan transfer energy into atoms in your hand. Convection happens in fluids like air or water. Warm air rises, cool air sinks, and energy gets moved around in bulk. But space removes most of that. There is no thick atmosphere between Earth and the sun. There is no large body of gas moving heat around like air moves heat in a room. So the main way the sun sends energy across space is radiation. Electromagnetic waves travelling at the speed of light, about 299,792 kilometers per second, or 186,282 miles per second. That is how sunlight gets here. It does not need air. It can move through vacuum. This is where most people make the next mistake. They think if space is cold, then it must be filled with something cold. But empty space is not cold in the way winter air is cold. Winter air feels cold because there are huge numbers of particles around you, and they can take energy from your body very efficiently. In space, there are so few particles that this kind of heat exchange becomes extremely weak. In low Earth orbit, the remaining gas is so thin that the density can be trillions of times lower than air at sea level. There simply are not enough particles there to behave like an atmosphere. That leads to the core answer. The sun heats objects, not emptiness itself in the way a furnace heats the air in a room. The sun sends radiation outward. That radiation keeps travelling until it hits something that can absorb it. A planet absorbs it. A spacecraft absorbs it. Dust absorbs it. A spacesuit absorbs it. Then those things heat up depending on what they are made of, how much light they absorb, and how well they can release that energy again. This is why two things in the same area of space can have very different temperatures. A spacecraft in sunlight can get extremely hot on the side facing the sun. A shaded surface right next to it can become extremely cold. That is not a small effect. On the Moon, surface temperatures in sunlight can reach about 127 degrees Celsius or 260 degrees Fahrenheit. In darkness, they can fall to about minus 173 degrees Celsius or minus 280 degrees Fahrenheit. Same location in the solar system, same general distance from the sun, but completely different temperatures depending on exposure. So the real problem with the original question is that it mixes together three different ideas as if they are the same. Temperature is one thing, heat transfer is another. The way something feels to your skin is another. Those are connected, but they are not identical. A metal object and a wooden object can be at the same temperature, and the metal still feels colder because it removes heat from your skin faster. In space, this difference becomes much more important. A place can receive intense solar radiation, but it still does not behave like a hot atmosphere because there is no dense medium spreading that energy around. That is why there is no contradiction here. The sun is hot, space is mostly empty. Radiation crosses that empty space very well, but the vacuum itself does not warm the way air would. So when people ask why space is cold if the sun is hot, the better version of the question is this: how does energy move when there is almost nothing there to carry it? And once you ask it that way, the whole topic opens up. Now, you're not just talking about the sun, you're talking about thermodynamics, radiation, vacuum physics, planets, spacecraft, astronaut survival, and even the history of the universe. The original question sounds basic, but it forces you to separate ideas that people normally blur together. And that is where the tension increases. Because once you stop thinking of space as a cold place and start thinking of it as a place where radiation dominates, you get to a more serious question. If heat in space does not work like heat on Earth, then what is heat actually? And what does temperature even mean when there is almost nothing there? You use the words heat and temperature like they mean the same thing, and that is exactly where this topic starts breaking apart. Because they are connected, but they are not the same. And if you mix them together, space stops making sense. Temperature is about how energetic particles are on average, how fast they are moving and jostling around. Heat is different. Heat is energy being transferred because one thing is hotter than another. That difference sounds small, but it changes everything. A tiny spark can be extremely hot, much hotter than bath water, but it does not contain much total energy, so it may not heat a large object much at all. A bathtub is much cooler, but it contains far more matter, so it can hold far more thermal energy overall. In space, this distinction is not optional. It is the whole game. A few particles can be moving incredibly fast, which means they have a high temperature, and still barely warm anything because there are too few of them to transfer much energy. That sounds strange at first. So here is the simpler version. Speed is not enough. Quantity matters too. If only a handful of particles hit you, they do not deliver much total energy. And that is one reason people get confused when they hear about very hot regions in space that do not behave like ovens. Now, the next problem is even bigger. You grew up inside a very misleading environment. On Earth, you live inside a thick atmosphere at around 101.3 kilopascals, or 14.7 pounds per square inch at sea level. That means molecules are everywhere. They are constantly colliding with your skin, your clothes, walls, water, metal, everything. Air makes heat exchange easy, so easy that your brain treats it as normal and universal. But it is not universal. It is a special case. That is why a room heats up the way it does. Sunlight comes through a window, the floor warms up, the air touching the floor warms up, and then that warmer air starts moving. Hot air rises, cooler air sinks, and suddenly energy is being spread through the room. You're not just being warmed by sunlight anymore. You're inside a whole system that is redistributing energy for you. Earth does that constantly. The sun heats the ground, the oceans, and the surface, and then the atmosphere takes over and moves that energy around. Remove the air, and that familiar system partly collapses. In space, conduction is weak unless objects are actually touching. Convection is basically absent because convection needs a fluid, like air or water, and vacuum is not a fluid. So two of the three main ways heat moves in daily life either vanish or become severely limited. That leaves one dominant pathway, radiation. And this is where the whole structure becomes clear. There are three main ways heat transfer happens. Conduction is direct particle-to-particle transfer. Touch a hot pan and energy moves straight into your skin through contact. Convection is bulk motion in a fluid. Boil water and the hotter water rises while cooler water sinks. Radiation is different from both. Radiation does not need matter between the source and the target. It moves as electromagnetic waves, and that means it can cross empty space. That is how the sun reaches you. The sun is putting out an enormous amount of power, about 3.8 times 10 to the 26 watts. That number is so large it stops meaning anything by itself, but the point is simple. The sun is not weak, and the energy is not a small effect. It is streaming outward through space in every direction as radiation. But that does not mean the vacuum itself heats up the way gas would. The radiation passes through the vacuum, and heating happens when that energy gets absorbed by matter. There is a very useful clue hiding in something ordinary, a thermos. A vacuum flask works because it reduces heat transfer. Between the inner and outer walls there is often a near vacuum layer. That near vacuum makes conduction and convection much weaker. Your coffee stays hot longer, not because the laws of physics stop working, but because two major routes for energy loss have been blocked. Less matter means fewer collisions. Fewer collisions mean less heat transfer through direct contact or moving fluid. That is why a thermos is such a good clue for space. Space is not filled with cold air. It is much closer to the empty layer inside a vacuum flask, except on a vastly more extreme scale. And that changes the entire thermal environment. You do not have a medium around you helping heat spread smoothly. You mostly have radiation coming in, radiation going out, and solid objects conducting heat internally if they are connected. But vacuum does not stop radiation, and that is the next thing people miss. Radiation never stops. Every object above absolute zero emits electromagnetic radiation. Your body does it, Earth does it, the moon does it, a spacecraft does it, the sun does it intensely. So a spacecraft in orbit is never just sitting there in some simple cold background. It is in a constant energy balance. It absorbs sunlight, it absorbs infrared from Earth, it absorbs reflected sunlight from clouds, oceans, or the ground below. At the same time, it is radiating its own heat away into space. That is why spacecraft thermal control is so serious. Satellites are covered in reflective materials, white coatings, multi-layer insulation, and radiators for a reason. The job is not just to protect against cold, the job is to control how much radiation gets absorbed and how much heat gets emitted back out. A spacecraft can overheat or freeze, or do both in different parts at once if that balance is wrong. Surviving in space is really about managing the imbalance between incoming and outgoing radiation. And now you get to the hidden twist that makes the original question even less intuitive. Space is not one temperature. There is no single number you can give that solves it. When people ask, what temperature is space, they are usually asking for one clean answer, but physics does not give them one. The temperature depends on the object, its surface, its orientation, what it can see, what it absorbs, and what it emits. A dark object near Earth in the direct sunlight can settle near temperatures around or above 120 degrees Celsius, or 248 degrees Fahrenheit, depending on its properties and how it is facing the sun. Put a similar object in shadow and it can drop below minus 100 degrees Celsius or minus 148 degrees Fahrenheit. So when people say space is cold, they are really compressing a much more precise idea into a simple phrase. What they usually mean is that if an object is not receiving enough incoming energy, it will keep radiating heat away and can become extremely cold. And that creates the real tension going forward. If heat is not just hot stuff, if temperature is not the same as total energy, and if space does not even have one fixed temperature, then the next question becomes unavoidable. What happens when you put those rules into a place that is almost completely empty, where even the idea of surrounding temperature starts to fall apart? Space is not just empty, it is empty on a scale that your intuition is not built to handle. And until that really sinks in, the rest of this topic keeps sounding wrong. When people hear vacuum, they usually picture a container with the air pumped out, maybe a lab chamber, maybe something close to perfect emptiness. But even the best vacuum chambers humans make on Earth are still crowded compared with real space. In deep space, particle density can drop to just a few atoms per cubic centimetre. In interstellar space, the average can be closer to about 1 atom per cubic centimetre, even though it varies a lot from place to place. Compare that with air at sea level, which has roughly 10 to the 19 molecules in the same volume. That gap is so huge that your normal instincts about heating and cooling stop being useful. That is the whole point here. On Earth, heat transfer feels normal because matter is everywhere. Air surrounds you, presses on you, moves around you, and constantly exchanges energy with you. In space, that support system is almost completely gone. So when you ask why space is cold, the answer is not just that the sun's radiation works differently. The answer is also that there is almost nothing out there to behave like an atmosphere in the first place. And once you remove almost all the particles, the next consequence follows immediately. Fewer particles means fewer collisions. That sounds obvious, but it is one of the most important ideas in the entire script. A hot oven roasts you because hot air molecules are hitting your skin in massive numbers over and over, while hot walls also add radiant heating. In other words, you're inside a dense environment that is constantly transferring energy into you from multiple directions. Space does not do that. In space, there is no thick cloud of particles surrounding you and driving everything toward one shared temperature. Even if the few particles around you are energetic, there are too few of them to transfer much total heat. That is why in orbit, astronauts and engineers do not think in terms of air temperature the way you do on Earth. They think in terms of radiation balance, what is being absorbed, what is being emitted, what is in sunlight, what is in shadow, what sees Earth, what sees deep space. And this is where the subject gets more extreme because the sun itself gives you a version of this paradox. The sun's outer atmosphere, the corona, can reach temperatures of around 1 million to several million Kelvin. That is far hotter than the visible surface of the sun. And if you hear that without context, it sounds like the entire argument should collapse. If the corona is that hot, then shouldn't everything near it be instantly destroyed? But the corona is also extremely thin. That is the key. Its particles have very high energies, yes, but there are not enough of them packed together to behave like a dense blast furnace. So even though the corona is hotter in the sense of particle energy, the total heat available for transfer can be much lower than your instincts expect. This is exactly why temperature by itself can mislead you. High temperature does not automatically mean intense heating of everything nearby. Density matters too. How much stuff is actually there matters too. This is one of the hardest parts for people to accept because in normal life, hot things tend to also be dense enough to dump energy into you quickly. In space, those two ideas can split apart. A thin gas can have very fast particles and still not warm an object efficiently, simply because there are too few particles hitting it. So when physicists say a sparse gas is hot, you'll have to listen carefully. They often mean the particles in that gas have high average kinetic energy. That is a real statement, but it does not automatically tell you how strongly that gas will heat something nearby. If almost no particles are present, then the actual rate of energy transfer can stay very small. That is why the word temperature can mislead you in thin gases. Speed matters, but amount matters too. If one fast-moving particle hits you, that is not the same as trillions of particles hitting you every second. In simple terms, one baseball and one truck are not equally dangerous just because both are moving fast. The energy transfer depends on how much stuff is involved, not just how fast each piece is moving. Now bring that back to the space around Earth. Earth's atmosphere can trap, absorb, and redistribute heat because it has enough mass, enough collisions, enough absorption, and enough pressure differences to move energy around in a continuous system. Warm air rises, cooler air falls, winds form, weather happens, energy gets spread. That whole process depends on there being enough matter for those mechanisms to work. The near vacuum in orbit does not do that well at all. Low Earth orbit is not perfect emptiness, but it is empty enough that spacecraft designers mostly treat the environment as radiative, not atmospheric. That changes everything. A satellite can move from direct sunlight into Earth's shadow and experience major thermal swings in only tens of minutes. Not because the surrounding air suddenly changed temperature, but because the radiative input changed fast, while the vacuum did almost nothing to smooth that change out. And that leads to one of the most important lines in this whole topic. Nothing turns out to be an active thermal environment. That sounds contradictory, but it is correct. Space is not a passive freezer. It is an environment where the missing matter forces radiation to dominate almost everything. Once that happens, details that seem minor on Earth become critical in space. Surface coatings matter. Geometry matters. Which side faces the sun matters. Which side faces deep space matters. Whether a spacecraft is spinning matters. Whether a panel is shiny or dark matters. How well a surface emits infrared radiation matters. In vacuum, these are not small engineering choices. They are survival variables. That is why all these things can be true at the same time without contradiction. The sun can be hot. A spacecraft surface can be hot. A shadowed panel on that same spacecraft can be dangerously cold. Deep space can sit near the background temperature of about 2.7 Kelvin. And all of it can coexist because vacuum does not force temperatures to equalize the way an atmosphere does. So now the tension gets sharper again. If the emptiness of space is the real reason your intuition keeps failing, and if even hot gas can fail to heat efficiently when it is too thin, then the next question becomes unavoidable. If the vacuum is not carrying heat around like air does, then what is the sun actually sending through space, and how does that energy reach you at all? The sun is blasting energy across space every second, so why does that not turn the vacuum between here and there into a giant furnace? That is the next step, and this is where the answer becomes very precise. The sun reaches you through space in one main way: radiation. Sunlight is not hot air from the sun. The sun is not blowing warmth at Earth the way a heater or a hairdryer blows warm air into a room. There is no stream of hot gas filling the whole distance between the sun and Earth and making space itself feel warm. What actually leaves the sun is electromagnetic radiation. That includes gamma rays, X-rays, ultraviolet, visible light, infrared, radio waves, and more. Most of the energy that matters for heating Earth arrives mainly as visible light, infrared, and some ultraviolet. Those photons leave the sun and cross nearly 150 million kilometers, or 93 million miles, of vacuum in about 8 minutes 20 seconds. That is how the sun reaches you. Not by warming the emptiness in between, but by sending radiation through it. That distinction sounds simple, but it destroys a very common mistake. People picture all that solar energy as if it should build up in space the way heat builds up in a room. But a room heats that way because air is there to absorb energy and pass it around. Space does not do that. Radiation moves through it, fast, until something intercepts it. So how much energy are we talking about really? At Earth's average distance from the Sun, the incoming solar power on a surface facing the Sun is about 1,361 watts per square metre outside the atmosphere. In imperial terms, that is about 126 watts per square foot. That value is called the solar constant, even though it changes slightly with Earth's distance from the Sun and with solar activity. The important part is the scale. That is a lot of energy. This is not a weak trickle. This is a major flux of power hitting every square metre that faces the Sun directly. But again, that does not mean empty space becomes an oven. It means any object that intercepts that flow can absorb some of it and heat up. That is the whole rule. The Sun is not heating space the way a stove heats the air in a kitchen. It is delivering energy to surfaces and particles that get in the way. And that makes absorption the real deciding factor. If a surface reflects almost all incoming sunlight, it heats much less. If it absorbs strongly, it heats much more. That is why spacecraft often look strange, with shiny foil, white panels, dark components, and dedicated radiator sections. Those are not random design choices. They are visible signs of thermal control. Different materials absorb different amounts of sunlight and emit heat differently, so engineers use surface properties as tools. On Earth, this is partly hidden from you because air and water blur the picture. Oceans store heat, clouds reflect sunlight, winds move energy around, and the atmosphere softens the direct link between sunlight and surface temperature. In space, that softness is mostly gone. The radiative physics is exposed more directly. What you absorb, you eventually have to get rid of. If you absorb too much and cannot emit it fast enough, you overheat. If you stop receiving enough incoming energy while still radiating outward, you cool rapidly. And then there is the next rule that breaks intuition even more. The sun does not heat all of space equally. Radiation spreads out as it travels. As distance increases, the same energy is spread over a larger and larger area. So if you double your distance from the sun, the intensity drops to 1/4. Triple the distance and it drops to 1/9. This is the inverse square law, and it is one of the reasons the solar system is not thermally uniform. This is why Mercury and Neptune live in completely different thermal realities. Mercury orbits at roughly 58 million kilometers, or 36 million miles, from the Sun. Neptune sits around 4.5 billion kilometers, or 2.8 billion miles, away. By the time sunlight reaches Neptune, it is only about 1/900th as intense as it is at Earth. The Sun is still the same Sun. It is still extremely hot, but distance spreads that energy out so much that the heating effect becomes far weaker. That matters because people often ask the wrong version of the question. They ask why the Sun does not make all nearby space hot, as if nearby is one simple category. But the solar system is enormous, and radiation weakens with distance very quickly. Even around Earth, the heating depends strongly on what direction a surface faces, whether it is in light or shadow, and what it is made of. That is why radiation heats things unevenly and selectively. A person in space would not heat uniformly. One side could be facing direct sunlight, another side could be shaded, a white suit could reflect a lot of incoming energy, a darker section could absorb more, a visor could block some intense radiation. A surface turned toward deep space could lose heat by radiation much faster than a nearby surface turned toward the sun. So when someone asks, what temperature is it in space, the question itself is already too vague to answer cleanly. In space, temperature becomes geometry dependent. Two surfaces only inches apart can differ by huge amounts because one is exposed to intense sunlight and the other is seeing darkness. That is not a rare edge case, that is normal space behaviour. On the International Space Station, thermal design is a constant fight against uneven heating. Different parts of the station see different sources of radiation, different shadow conditions, and different thermal loads, so keeping everything in safe ranges takes continuous engineering. And none of this is guesswork. We are not inferring the sun's energy output only from theory and then building stories around it. Satellites directly measure solar irradiance. Solar observatories measure the sun's spectrum across many wavelengths. Lunar temperatures have been measured by landers and orbiters. Spacecraft thermal systems are designed from direct observations and tested against real environments. We know the energy is there, that part is not mysterious. So the mystery was never whether the sun sends enough energy. It absolutely does. The real mystery was why that energy does not make the vacuum itself behave like a hot fluid. And now the answer is much sharper. Radiation crosses the vacuum very well, but the vacuum itself does not absorb, store it, and redistribute that energy the way a dense gas would. Heating still depends on matter. Something has to intercept the radiation, absorb it, and then re-emit it. And that is where the tension gets worse, because now you know the sun can deliver huge amounts of energy across empty space, and you know that energy can hit one surface while missing another only a short distance away. So the next question is not whether space can be hot or cold. The next question is how something in space can be pushed toward both extremes almost at once, how one side can bake while another side freezes. This is where the whole question stops feeling simple, because space is not just cold and it is not just hot, it can force both conditions onto the same object at the same time. That is not science fiction, and it is not an exaggeration. In low Earth orbit, a surface in direct sunlight can go above 120 degrees Celsius or 248 degrees Fahrenheit, while a shaded surface nearby can drop below -100 degrees Celsius or -148 degrees Fahrenheit, depending on the material and the situation. So when something enters space, it is not entering one clean thermal environment. It is entering a constant fight between incoming radiation and outgoing radiation. That is the part most people do not expect. On Earth, air smooths things out. It spreads heat, slows down extreme differences, and keeps nearby objects from drifting too far apart in temperature too quickly. In space, that smoothing system is mostly gone, so the side facing the sun can absorb energy hard and fast, while the side in shadow can keep losing energy with very little coming back. That is why the temperature contrast can become so severe, and sunlight is not gentle in that environment. If a surface faces the sun and absorbs a lot of radiation, it can heat up rapidly because there is no surrounding air carrying that heat away through convection. On Earth, the air acts like a moderator. It takes some heat from a hot surface and redistributes it. In space, that help is gone. Heat can still move through the object itself by conduction, and it can still be emitted away as infrared radiation. But those processes may not keep the temperature even across the whole structure. So parts of a spacecraft can become much hotter than other parts, very quickly. That creates real engineering problems. Electronics have safe operating ranges, batteries have safe operating ranges, sensors do too. Fuel lines, valves, seals, and structural materials all respond differently to heat. A hotspot is not just uncomfortable, it can damage equipment, shorten mission life, or cause a system to fail completely. So one of the core jobs in spacecraft design is stopping those temperature differences from getting out of control. Now the other side of the problem is just as serious, because shadow in space is not just cool, it can be deadly cold. If a surface moves into shadow, especially if it is facing deep space instead of a warmer object like Earth, it keeps radiating energy outward, but now it receives far less incoming energy in return. That means its thermal losses continue while its thermal gains collapse. Once that happens, temperature can drop fast. That is why darkness in space is such a big deal. In sunlight, energy is constantly arriving. In shadow, that stream can vanish almost completely, while radiative loss continues. If more energy is leaving than arriving, the object cools, and it keeps cooling until it reaches a new balance. That is one reason the Moon has such extreme temperature swings. With almost no atmosphere, the surface heats directly under sunlight, then cools hard in darkness because there is almost nothing there to hold on to or move that energy around. And this is where astronauts come into the picture, because a spacesuit is not just protective clothing. It is a personal life support machine and a personal thermal control system. An astronaut does not survive outside a spacecraft by wearing something like a winter jacket. A spacesuit has to regulate pressure, oxygen supply, carbon dioxide removal, humidity, and protection from micrometeoroids, but it also has to control temperature very carefully. That becomes harder because the astronaut is generating heat too. During a spacewalk, a person can produce hundreds of watts of metabolic heat simply by moving and working. That body heat has to go somewhere. On Earth, your body can dump heat into the air around you through convection, and sweat can evaporate in a familiar way. In vacuum, that normal cooling pathway is gone, so the suit has to actively remove body heat. That is why astronauts wear liquid cooling garments with water running through small tubes. The water carries heat away from the body because vacuum itself is very poor at cooling you directly. This is another place where movies get the physics badly wrong. Vacuum does not suck heat out of you the way icy wind does. In a cold wind on Earth, moving air strips heat away from your skin quickly because convection is strong. In vacuum, that convective cooling disappears. So a person exposed to vacuum would not instantly freeze solid the way movies often show. The danger is still extreme, but it comes from the wrong things first. A bare human in vacuum would be in catastrophic danger from pressure loss, lack of oxygen, gas expansion effects, and severe biological damage long before heat loss becomes the main issue. Thermally, the body would lose heat mostly by radiation, and radiation is slower than the dramatic instant freezing version people are used to seeing on screen. So the threat is real, but the mechanism is different. It is not a giant freezer. It is a hostile environment where the normal heat transfer rules you rely on have been stripped away, and that changes what survival means in space. You're not just trying to stay warm against one cold background. You're trying to stay in thermal balance inside an environment that can heat one side of you intensely, while another side keeps dumping energy away. You may be absorbing sunlight, reflecting some of it, radiating your own heat away, gaining infrared from nearby structures, and losing energy into darkness all at the same time. That is why thermal engineering is such a central part of space exploration, even though it gets much less attention than rockets or engines. The sun is hot, space is cold, and the deeper truth is that both of those facts can act on the same spacecraft, the same suit, even the same astronaut at once. And once you understand that, the next step gets even more serious. Because there is one place close to us that proves this whole argument directly, with measured temperatures, no atmosphere, and nowhere to hide from the physics. The moon gives you the cleanest proof in the entire solar system, because it removes almost every excuse your intuition wants to use. If you want to know what sunlight does when there is almost no air, no weather, no real atmospheric buffering, and no easy way to spread heat around, the moon is the test case. It has almost no atmosphere in any normal Earth sense. That means there is no substantial layer of gas to redistribute heat through convection, and no thick blanket to trap infrared radiation the way Earth's atmosphere does. So the lunar surface responds to sunlight and darkness in a much more direct way. And this is not a guess, it is measured. Near the lunar equator, daytime temperatures can climb to about 127 degrees Celsius or 260 degrees Fahrenheit. At night, they can fall to about minus 173 degrees Celsius or minus 280 degrees Fahrenheit. That is an enormous swing, and it happens on a world that sits in almost the same solar neighbourhood as Earth. That should immediately tell you something important. The question was never just about being near the sun. If distance from a hot star were the only thing that mattered, then the moon should behave much more like Earth. But it does not. It gets intensely hot in daylight and brutally cold in darkness, because it lacks the systems that make Earth thermally stable, and the reason is direct. When sunlight hits the moon, the surface absorbs energy and heats up. When sunlight is gone, the surface keeps emitting thermal radiation away into space, and with almost no atmosphere to slow that loss or move heat around, the temperature drops hard. That is the whole mechanism in a very exposed form. Earth has oceans, clouds, winds, greenhouse gases, and large thermal inertia. The moon has almost none of that. It is a much simpler thermal system, and because it is simpler, it gives you a cleaner answer. The sun heats surfaces directly. It does not turn the vacuum between those surfaces into warm, comfortable air. The moon proves that in a way no analogy can. You can point to actual measured temperatures and say, this is what sunlight plus vacuum plus almost no atmosphere really looks like. And the moon makes the problem even more extreme because its day and night are so long. A full lunar day-night cycle is about 29.5 Earth days. That means one sunrise to the next takes about that long too, so a location near the equator can spend roughly 2 Earth weeks under continuous sunlight, then roughly 2 Earth weeks in darkness. That matters because temperature is not just about what is happening right now, it is also about how long heating or cooling continues. So on the moon, a surface is not just getting a short burst of sunlight and then cooling down a few hours later. It can sit under direct solar radiation for around 2 weeks, building up heat, and then spend around 2 weeks radiating that heat away into darkness. That is one reason the swings are so severe. There is no fast atmospheric reset, no strong weather system, no ocean currents evening things out, and no thick blanket of air holding on to the energy. This is also where the moon stops being a distant science example and becomes a direct engineering problem. Apollo had to deal with this in real hardware, not just in theory. Spacesuits had thermal limits. Lunar modules had thermal limits. Electronics, batteries, and sample containers all had thermal limits. Astronauts were not operating in some simple cold space environment. They were in a highly uneven radiative environment where sunlight angle, local shadow, surface reflectivity, and dust all mattered. That is why mission planning paid close attention to the position of the sun. The angle of the sunlight affected how much heating surfaces received. The timing of activity mattered. Where something sat in light or shadow mattered. The material properties of equipment mattered. None of that is extra detail. It is the direct consequence of working on an airless world where radiation dominates and thermal balance can change quickly depending on exposure. And the Moon has an even more extreme version of this at the poles. Some craters near the lunar poles are so deeply shadowed that sunlight may never reach parts of them at all. These permanently shadowed regions can stay below about 40 Kelvin, which is around minus 233 degrees Celsius or minus 387 degrees Fahrenheit. That is colder than Pluto's average surface temperature. So even this close to the Sun, in Irhofthe's own neighbourhood, there are places cold enough to preserve water ice and other volatile materials for extremely long times. That matters scientifically, but it also matters practically. Those ultra-cold traps are one of the major reasons lunar polar exploration is so important. If water ice survives there, it can potentially support future missions through life support and fuel production. So the original question, why is space cold if the Sun is hot, ends up connecting directly to one of the most important practical issues in future space exploration. The cold is not just a curiosity, it creates storage vaults for resources. And that brings you to the lesson the Moon makes impossible to avoid. The Moon is basically at Earth's distance from the Sun. Same general neighbourhood, same general solar input scale. Yet it swings between extreme heat and extreme cold because exposure and heat retention matter more than your intuition expects. The Sun provides energy, yes, but temperature depends on what absorbs that energy, how long it absorbs it, how much of it is reflected, and how efficiently it can radiate energy away afterward. That is why the Moon destroys the simple idea that being near the Sun means everything nearby should just be hot. It shows, with measured numbers and real missions, that sunlight alone does not create a stable, warm environment. Matter, atmosphere, heat storage, and heat redistribution matter just as much. And that raises the next question. Because if the Moon proves Earth is thermally unusual, then what exactly is Earth doing differently? If our planet sits in the same solar neighbourhood but does not swing like the Moon, then the real answer has to be in the atmosphere, not in the vacuum around it. Earth is not warm because the space around it is warm, and that is one of the most important corrections in this whole topic. If you miss that, you miss the real reason our planet feels livable while the Moon does not. If Earth had no atmosphere, its average effective radiating temperature would be around 255 Kelvin, which is about minus 18 degrees Celsius, or 0 degrees Fahrenheit. But the actual global average surface temperature is closer to about 288 Kelvin, or 15 degrees Celsius, 59 degrees Fahrenheit, depending on the dataset and the time period. That difference, roughly 33 degrees Celsius, is the greenhouse effect. Not a slogan, not an opinion, not a vague idea, but a measured result of how certain gases absorb and re-emit infrared radiation. That matters because it tells you right away that sunlight alone does not set Earth's surface temperature. The Sun provides the incoming energy, yes, but Earth's atmosphere changes what happens to that energy after it arrives. Without that atmospheric system, Earth would be far colder on average. So when people ask why space is cold if the Sun is hot, one hidden part of the answer is this. Earth feels warm because it has built-in thermal infrastructure. The vacuum around Earth is not doing that job for us, and that infrastructure is not just air sitting there passively. Earth's atmosphere and oceans store energy, move energy, and redistribute energy. Sunlight heats the ground and oceans. The surface then emits infrared radiation upward. Greenhouse gases in the atmosphere absorb some of that outgoing infrared and re-radiate it. Winds move heat sideways across the planet. Ocean currents move huge amounts of heat over long distances. Water vapour, clouds, and evaporation all add more complexity. That is why nights on Earth are not like nights on the Moon. It is why coastal regions often have milder temperatures than inland regions. It is why humid places usually cool differently from dry deserts. Earth does not simply receive sunlight and then respond like bare rock in vacuum. It takes a radiative input and turns it into a full climate system. That system is one reason your ordinary experience can be so misleading when you think about space. On Earth, warm air rises, and cool air sinks. That sounds basic, but it changes almost everything. A patch of ground sits in sunlight, it warms up, then the nearby air warms too. That air moves, mixes, and spreads the energy. So when you feel warmth outdoors, you're rarely experiencing radiation alone. You're usually inside a whole chain of processes involving conduction, convection, evaporation, cloud cover, humidity, and moving air. In space, there is no comparable ocean of air around a spacecraft or a moon rock. There is no natural convection system stepping in to smooth out the result. That is why the direct effect of absorption stands out more clearly. If a surface absorbs energy, it heats. If it stops receiving enough incoming energy, it cools by radiation. There is much less environmental moderation. Spacecraft engineers have to create that moderation artificially with insulation, radiators, heat pipes, coatings, and active cooling systems, because the environment will not do it for them. And even on Earth, the picture is more complicated than just greenhouse gases. The planet reflects about 30% of incoming sunlight back to space on average. That is Earth's planetary albedo. Clouds reflect a lot. Snow and ice reflect a lot. Deserts, forests, oceans, and cities all interact with sunlight differently. Bright surfaces tend to reflect more and absorb less. Darker surfaces absorb more and warm more. That same logic shows up everywhere else in space. A bright spacecraft coating reflects sunlight better than a dark one. A bright, icy world responds differently to sunlight than a dark, rocky one. The difference on Earth is that our atmosphere and oceans blur some of these direct effects by moving heat around and storing it in different forms. In space, with no thick atmosphere involved, those raw radiative differences stand out much more sharply. And here is the part many people do not think about enough. Earth is constantly radiating energy out to cold space. Right now, all the time, our planet is losing energy upward in the form of infrared radiation. The reason Earth does not keep heating forever is that over time, incoming solar energy and outgoing thermal radiation move toward balance. The atmosphere affects how quickly and from where that radiation escapes. Clouds matter. Greenhouse gases matter. The structure of the upper atmosphere matters. But the key point stays the same. Earth is warm because it has a system that absorbs incoming energy, stores part of it, moves it around, and slows down how quickly it escapes. Earth is not warm because the vacuum outside it is warm. In fact, the planet is constantly radiating toward a cold background. Habitability depends on what happens inside the planetary system, not in the emptiness around it. And that is why this question is much bigger than it first sounds. Once you ask why space is cold while the sun is hot, you are really asking why planets can end up so different from each other. Why one rocky world becomes habitable, why another becomes a furnace, why another becomes a frozen desert. The same basic physics controls all of it, but different planets get different outcomes depending on atmosphere, pressure, chemistry, clouds, albedo, rotation, and heat storage. So this is no longer just a question about outer space. It's a question about why Earth works at all, why Venus became a pressure cooker, why Mars struggles to hold on to warmth, why the Moon cannot buffer temperature swings, and that means the next step becomes unavoidable. If Earth's atmosphere explains why our planet stays relatively warm, then the fastest way to expose the full rule is to compare Earth with nearby worlds that got completely different results under the same sun. One sun, 3 rocky planets, 3 completely different thermal realities. That is where this stops looking like a strange question and starts looking like a rule of the universe. Start with Mercury. It is the closest planet to the Sun, orbiting at about 58 million kilometers or 36 million miles. So your first instinct says Mercury should just be hot, full stop. But that is not what happens. On the day side, temperatures can climb to around 430 degrees Celsius or 800 degrees Fahrenheit. On the night side, they can fall to around minus 180 degrees Celsius or minus 290 degrees Fahrenheit. That is a massive swing. Why does that happen on the planet closest to the Sun? Because Mercury has almost no substantial atmosphere. It gets intense sunlight, yes, but it does not have a thick enough atmospheric system to hold onto that energy and spread it around. So when sunlight is hitting the surface, the ground gets extremely hot. When that sunlight is gone, the surface loses heat fast by radiation. Mercury is one of the clearest possible examples of the point you have been building. Solar heating alone does not create thermal stability. Now go to Venus, and the whole story flips. Venus is farther from the Sun than Mercury, orbiting at about 108 million kilometers, or 67 million miles from it. It receives about twice the solar energy Earth receives, so yes, it starts with a stronger solar input than Earth. But distance is not the main reason Venus is so extreme. The real reason is the atmosphere. Venus has a massive, dense, greenhouse-rich atmosphere, with a surface pressure about 92 times Earth's sea level pressure. And the result is brutal. Surface temperatures average around 465 degrees Celsius, or 869 degrees Fahrenheit. That is hot enough to melt lead. So Venus gives you the opposite lesson from Mercury. Mercury shows that strong sunlight does not guarantee stable warmth. Venus shows that an atmosphere can trap energy so effectively that it overwhelms what your distance-based intuition expects. That matters because it sharpens the original answer. The warm environment on Venus is not coming from warm space around the planet. It is coming from the planet's own atmospheric system. The vacuum outside Venus is not acting like a hot oven. Venus built its own oven. Then there is Mars, and Mars gives you a third outcome. It is farther from the Sun than Earth, at roughly 228 million kilometers, or 142 million miles on average. So it starts with weaker sunlight. On top of that, its atmosphere is thin, with a surface pressure typically less than 1% of Earth's. That means Mars has some atmosphere, but not enough to do the kind of thermal work Earth's atmosphere does. So what happens? Near the equator, daytime temperatures can sometimes rise above freezing, but at night, temperatures can drop hard, often to minus 70 degrees Celsius, or minus 94 degrees Fahrenheit, and sometimes colder. Mars sits in an important middle category. It is not like Earth, because its atmosphere is too thin to provide strong thermal buffering. But it is also not exactly like the Moon or Mercury, because there is still some atmosphere there. It is enough to matter, but not enough to stabilize the planet the way a thick atmosphere would. And this is one of the hardest hitting lines in the whole script because it is so simple. One sun, 3 rocky worlds, 3 radically different thermal outcomes. Mercury shows what happens when intense sunlight hits a world with almost no atmosphere. Venus shows what happens when an atmosphere traps energy with extreme efficiency. Mars shows what happens when the atmosphere is too weak to hold on to much heat. The sun is only part of the story. The planet itself decides what that energy becomes. That is the rule your audience needs to feel at this point. Sunlight provides energy, but planets decide the outcome through atmosphere, pressure, composition, reflectivity, rotation, and heat storage. That is why the same star can produce a world that swings between furnace and deep freeze, a world that stays hot enough to melt lead, and a world where daytime and nighttime can feel like 2 different planets. And none of these are just theoretical classroom examples. These are measured worlds. Mercury's thermal extremes were observed by spacecraft like Messenger. Venus's surface conditions were measured directly by Soviet Venera landers, and then studied further by later missions. Mars is constantly monitored by orbiters, landers, and rovers measuring temperatures, pressure, dust, and atmospheric behavior. So when you say the sun is hot and space is cold, you are not talking about a word puzzle. You're talking about a set of real, observed planetary outcomes. That is why this question becomes much bigger than it first sounded. It is no longer just why is space cold if the sun is hot? Now it is what actually controls temperature on worlds exposed to the same star? And the answer is not just distance, it is atmospheric thickness, atmospheric composition, albedo, heat capacity, surface properties, and how energy gets absorbed and released over time. So by now the phrase "space is cold" should start sounding incomplete. It is not wrong, but it is incomplete. It tells you that vacuum does not distribute heat for free. It tells you that sunlight alone is not enough to explain what a world feels like. And that opens the door to an even bigger layer of the answer, because once you move beyond planets and ask what temperature the universe itself has, you run into something even stranger. Space is not at absolute zero, and the whole cosmos is still carrying a measurable thermal background from the early universe. Space is not at absolute zero, and that matters more than most people realize. People say space is absolute zero cold all the time, but that is wrong. The universe actually has a measurable background temperature, and one of the biggest reasons we know that is the cosmic microwave background, the CMB, the leftover radiation from the early universe. Today its temperature is about 2.725 Kelvin, which is about minus 270.425 degrees Celsius, or minus 454.765 degrees Fahrenheit. That is only about 2.7 degrees above absolute zero. In human terms, that difference sounds tiny. In cosmology, it is enormous. And this is not some abstract background idea physicists keep around for decoration. The CMB is observational evidence. It was discovered in 1965 by Arno Penzias and Robert Wilson when they found a persistent microwave signal coming from every direction. Later, missions like COBE, WMAP and Planck measured it in far greater detail and showed that it matches the picture of a much hotter, denser, early universe. So when you ask what temperature space is, there actually is a meaningful background answer. It is just not the answer most people think they're asking when they picture cold space. So then the obvious question is, if the sun is so powerful, why does it not overwhelm that background everywhere? Because the sun dominates locally, not universally. Near Earth, solar radiation is the main radiative input for anything exposed to it. Near other stars, those stars dominate their local surroundings too. But go far away from stars, planets and bright dust clouds, and the thermal background drops. In those darker regions of interstellar or intergalactic space, the CMB becomes part of the dominant background radiation field. So the universe has layers of thermal context. Local stars matter, galactic dust matters, hot gas matters, cosmic rays matter, and underneath all of it sits this relic radiation from the early universe. And this is one of the most important turns in the whole video. Cold does not mean radiation free. That is the mistake people keep making. Anything above absolute zero emits radiation. The only question is what kind of radiation and how much. The CMB peaks in microwave wavelengths because its temperature is so low. The sun peaks in visible light because its surface is so much hotter. Same underlying physics, completely different temperature range, completely different spectrum. So the universe does not switch from hot to cold by turning radiation off. It changes the energy distribution of the radiation. That also means the coldness of space has a history. The background of the universe used to be much hotter. As the universe expanded, the wavelengths of that ancient radiation stretched out and lost energy. Roughly 380,000 years after the Big Bang, the universe had cooled enough for neutral atoms to form, and light could finally travel freely instead of being trapped in the earlier hot plasma. Since then, cosmic expansion has kept stretching that light until it became the microwave background we measure today. So modern space is cold partly because the universe has been cooling for billions of years as it expands. And now the original question gets much bigger than the solar system. Space is cold not just because vacuum behaves differently from air, even though that part is true. Space is also cold because the universe itself has a thermal history. The sun is hot because stars are dense, gravitationally compressed nuclear furnaces. Interplanetary space is cold because it is mostly empty and does not redistribute heat like an atmosphere. And the cosmic background is cold because the universe has expanded, aged, and cooled over time. So a question that sounded simple at the start is now touching the early universe itself. And this is where the tension rises again, because the story still is not finished. Once you accept that space can be cold even while being full of radiation, There is an even stranger problem waiting right next door. The sun's outer atmosphere is hotter than the sun's visible surface, and somehow that still does not turn surrounding space into a giant blast furnace. That sounds even more wrong, and that is exactly why it is the next piece of the answer. The sun gets stranger the closer you look at it, because its outer atmosphere is hotter than its visible surface. That sounds backward, because it is backward. The sun's visible surface, the photosphere, is around 5,500 degrees Celsius, but the corona above it reaches temperatures of about 1 million to several million Kelvin. Scientists know this from spectroscopy and from solar observatories that measure the sun across many wavelengths. So the original question does not get simpler when you look at the sun in more detail. It gets worse. The outside is hotter than the layer below it, and that is exactly why this section matters. The corona is a plasma, but it is a very thin plasma. Its particles have extremely high energies, which is why its temperature is so high, but the density is low. That means a hotter region does not automatically behave like a dense hot object that can dump huge amounts of heat into everything nearby. This is the same trap again. Temperature alone is not enough, density matters, particle count matters, the way energy is transferred matters. If you ignore that, the corona sounds like it should instantly solve the mystery by making everything around the sun act like a furnace. It does not. Then you get to the solar wind, and the same lesson hits even harder. The sun continuously sends out a stream of charged particles called the solar wind, flowing through the solar system at speeds often around 400 to 800 kilometers per second, roughly 250 to 500 miles per second. That is extremely fast by human standards. But fast is not the same as dense. The solar wind is sparse, so it is not like standing inside a roaring, dense blast of hot gas. It is an energetic plasma flow moving through mostly empty space, and that difference is everything. That is why space weather is dangerous for reasons that are more specific than simple heat. Solar flares and coronal mass ejections can damage satellites, interfere with radio communication, expose astronauts to higher radiation risk, and induce harmful electrical currents in power systems on Earth. The danger is electromagnetic and particle radiation driven. It is not just that space gets hotter. The sun changes the plasma environment, the magnetic environment, and the radiation environment. That is a much more serious and much more accurate way to describe the threat. And again, this is not guesswork. Missions like SOHO, SDO, Parker Solar Probe and Solar Orbiter from SEP have transformed solar physics by observing the sun remotely and, in Parker's case, directly sampling particles and magnetic fields in the corona. NASA states that Parker Solar Probe has flown through the sun's upper atmosphere, the corona, and taken in situ measurements there. ESA's Solar Orbiter is also designed to connect remote observations of the corona with in situ measurements of the solar wind around the spacecraft. These missions keep confirming the same basic point. The sun's environment is extremely energetic, but it does not behave the way human intuition expects from everyday hot objects in air. So the sun itself teaches the rule you need. First, the sun is hot, then its outer atmosphere is even hotter. Yet surrounding space is still mostly cold vacuum. That is not because the sun is weak, and it is not because the energy is missing. It is because high temperature is not the same thing as dense, efficient heating of everything nearby. The physics depends on transport, on how energy moves, what absorbs it, how dense the material is, and how effectively it can transfer that energy onward. That is the rule that keeps surviving every example. And now the next step becomes unavoidable, because once the sun itself has shown you that hot does not automatically mean easy to heat everything nearby, the focus shifts from physics to engineering. If space can bake one side of a machine, freeze another side, and expose both to violent radiation changes from the same star, then the next question is how spacecraft survive that at all. Every spacecraft is fighting a thermal war, whether people notice it or not. The public usually thinks spaceflight is mainly about engines, fuel and guidance. Engineers know that is only part of it. Near Earth, A spacecraft can move from full sunlight into planetary shadow and back again over and over. In low Earth orbit, one full orbit is about 90 minutes, so a vehicle can cycle through heating and cooling many times a day. That repeated change puts stress on structures, electronics, batteries, seals, and moving parts. Thermal control is not a side issue. It is one of the reasons spacecraft survive at all. And the reason this is such a hard problem is simple. You cannot rely on air to save you. On Earth, a laptop gets rid of heat using fans and surrounding air. In spacecraft, fans can still move air inside pressurized modules, but once the heat has to leave the vehicle, it cannot depend on convection into outside air because there is no outside air. It has to be carried to radiator surfaces and emitted away as infrared radiation. NASA's thermal control guidance states this directly. Spacecraft temperatures depend on how much heat is absorbed, stored, generated and dissipated, and radiators are a core part of rejecting that heat to space. That is why spacecraft use radiator panels, thermal pathways, and strict thermal zoning. That is also why materials matter much more than most people expect. Engineers care about absorptivity, how much sunlight a surface takes in, and emissivity, how effectively it radiates heat away. A surface that absorbs a lot of solar energy but also emits heat well behaves differently from one that reflects sunlight strongly but traps heat poorly. Multi-layer insulation, the shiny blanket-like material seen on many spacecraft, is there to reduce radiative exchange. White coatings can help reflect solar input. Specialized thermal finishes are chosen because the surface itself becomes part of the thermal control system. None of that is visual style, it is controlled radiation management. The James Webb Space Telescope is one of the clearest demonstrations of this. Webb's sunshield is about the size of a tennis court, and NASA says it reduces the temperature difference between the hot side and cold side by about 570 degrees Fahrenheit, or 299 degrees Celsius, across its 5 layers. NASA also states that the cold side operates around 40 Kelvin, about minus 233 degrees Celsius, or minus 388 degrees Fahrenheit, because the shield blocks sunlight, earthlight, and moonlight so effectively. That means one structure in space can maintain radically different thermal zones purely by controlling radiative exposure. That is your whole topic turned into hardware. The International Space Station proves the same rule on a human scale. The ISS uses an active thermal control system with ammonia cooling loops and large external radiators. NASA documents describe heated ammonia circulating through exterior radiators, where the heat is released by radiation to space. The station also uses insulation, heaters, and carefully designed thermal pathways because sunlight heats some parts strongly. Internal equipment and humans generate additional waste heat, and shaded areas can cool fast. So the ISS is not floating in one simple cold environment. It is constantly maintaining balance against uneven incoming and outgoing energy. And that is the final point of this section. Space exploration works because engineers learned the real answer, not because the environment is forgiving, and not because space is cold turned out to be simple. Measurements, equations, tests, and failures taught us that sunlight heats objects selectively, vacuum removes convection, and thermal survival depends on controlling absorption, emission, storage, and transport. Every successful spacecraft is proof that space near the sun is not simply hot. It is more complicated, more uneven, and more dangerous than that. And this brings you to the physics underneath all of it. Because once you see spacecraft surviving by controlling what they absorb and what they emit, the next question becomes the deepest one yet. What exact law connects a star, a planet, a spacecraft radiator, your own body heat, and even the background glow of the universe? Everything glows, even if your eyes cannot see it. That is the next law you need. Because once you understand it, the whole story about the sun, planets, spacecraft, and even the universe starts fitting together. When people hear the word glow, they usually think of visible light, something red hot or white hot. but visible light is only a small slice of the electromagnetic spectrum. Any object above absolute zero emits electromagnetic radiation. Human bodies do it mostly in the infrared. Earth does it mostly in the infrared. The Sun does it much more strongly and at shorter wavelengths because it is much hotter. NASA and ESA both describe this through blackbody radiation. Hotter objects emit more total energy, and their emission peaks at shorter wavelengths. That brings you to one of the most important laws in the whole subject, the Stefan-Boltzmann law. In plain language, it says the power radiated by a perfect emitter rises with the fourth power of absolute temperature. That fourth power dependence is huge. Double the absolute temperature, and the radiated power does not merely double, it goes up by 16 times. NASA's thermal engineering material uses this directly for spacecraft temperature estimates, and ESA explains the same point in its stellar radiation material. That is why the Sun radiates so fiercely, and it is also why objects in space can cool effectively by radiation when they are not absorbing too much incoming energy. Then there is Wien's law, which tells you where the peak of that thermal radiation sits in the spectrum. The hotter the object, the shorter the wavelength at which it emits most strongly. NASA and ESA both use blackbody curves to show this clearly. A hot object peaks at short wavelengths, a cooler object peaks at longer ones. So the Sun, with a photosphere around 5,778 Kelvin, peaks in the visible range. Earth, being much cooler, peaks in the infrared, and the cosmic microwave background, at 2.725 Kelvin, peaks in the microwave part of the spectrum. Same physics, three very different temperatures, three very different parts of the spectrum. And that is why there is no single temperature for space. What a real object settles to is an equilibrium temperature, the point where absorbed power matches emitted power. NASA's orbital thermal material explains this directly for spacecraft. The final temperature depends on incoming sunlight, the object's surface properties, and how effectively it radiates energy away. Orientation matters. Reflectivity matters. Emissivity matters. Internal heat generation matters. What the object can see matters too, whether that is deep space, Earth, the Sun, or a nearby structure. A rotating spacecraft can average out some heating. A surface locked in one direction may not. This is also why blackbody physics is so powerful in astronomy. Radiation carries temperature information. That is how astronomers estimate star temperatures from spectra. It is how they characterize planets and dust clouds. It is how we know the cosmic microwave background is 2.725 Kelvin. It is how Earth's effective radiating temperature is estimated at about 255 Kelvin, even while the average surface temperature is closer to 288 Kelvin because of the greenhouse effect. NASA and ESA sources make that chain very clear. The spectrum tells you the temperature, and the total radiation tells you how much energy is being emitted. So the big line underneath all the math is this: space decides temperature through radiation balance, not through the kind of everyday intuition you learned in air. Objects do not simply get hot because they are near something hot. They absorb, emit, reflect, rotate, enter shadow, leave shadow, and settle into a balance if conditions stay steady long enough. That is how a spacecraft survives. That is how planets differ. That is how stars, worlds, and the background universe all fit into the same set of rules. And once you accept that, the next question becomes even more personal, because it goes straight at one of the most persistent space myths. If vacuum changes heat transfer this much, then why do astronauts not instantly freeze the moment they are exposed to space? Movies get the first danger wrong, and that matters because it distorts the whole physics of space. The usual scene is instant freezing, like the vacuum itself is some kind of supernatural deep freezer. But that is not the first thing that would happen. In real vacuum exposure, the immediate dangers are lack of oxygen, pressure loss, gas expansion effects, and ebullition, which is when body fluids can begin to boil at low pressure. NASA's pressure suit history even describes a vacuum chamber incident where a subject exposed to near vacuum stayed conscious for about 14 seconds before losing consciousness. That tells you something very important right away. The timeline is dominated first by pressure and breathing failure, not by sudden thermal transformation. And the reason the movie version fails is that your body normally gets rid of heat through several routes at once. On Earth, you lose heat by radiation, convection, conduction, and evaporation. Moving air increases convective cooling. Sweat and evaporation matter a lot. NASA Human Thermal Control Material describes the human body as a continuous heat source that must reject metabolic heat even at rest, and that heat output rises sharply under activity. In vacuum, convection disappears because there is no surrounding air to carry heat away. Evaporation also changes radically because the pressure environment is no longer survivable. Radiation remains, but radiation alone is much slower than the instant flash freezing image people are used to. That leads to the next part people do not expect. In sunlight, vacuum can make thermal control harder in both directions. External surfaces can absorb significant solar radiation while your body is still producing its own heat. NASA's spacesuit material explains that astronauts wear a liquid cooling and ventilation garment under the suit, with water running through tubes across the body. That cooling system exists because astronauts can overheat during EVA from body heat and absorbed radiation, even while the outside environment may include very cold shadowed regions. So the problem is not simply space is cold, the problem is unstable thermal balance in an environment where your normal cooling pathways are gone. Real suit design makes this very clear. NASA describes the liquid cooling and ventilation garment as one of the first things astronauts put on, with hundreds of feet of tubing woven through it to carry away excess body heat. Outside that, the suit includes protective layers that help insulate the astronaut and guard against the environment. That is not what you build for a place that only threatens one kind of cold. That is what you build for a place where heat rejection, insulation, pressure control, and life support all have to work together at once. And the human survival data points reinforce the same lesson. NASA's pressure suit history notes that a near vacuum exposure left one subject conscious for about 14 seconds before blackout, and he later reported the sensation of water on his tongue beginning to boil. That is a direct reminder that low-pressure injury arrives immediately, while dramatic thermal effects do not dominate first. Brief vacuum exposure can be survivable if repressurization happens quickly enough, but it is still extremely dangerous. The danger is just not the simple movie danger. So the myth survives mostly because cold space sounds simple, while the real answer is more technical. But the real answer is also more unsettling. Space is not waiting to freeze you like a meat locker. It is an environment where the normal heat transfer rules you depend on vanish, pressure itself becomes a threat, and survival depends on wearing a small life support and climate control system around your body. That is more accurate, and it is also much harsher than the movie version. And now the scale gets even bigger, because once you understand that even a human body cannot depend on space to behave like cold air, the next question becomes unavoidable. If vacuum does not spread heat efficiently, then why is most of the universe cold on average even though stars are blazing all over it? Most of the universe is cold for a very simple reason that only sounds strange at first. The hot parts are real, but they are local. Stars are not spread evenly through space like heat in a pot of soup. They are compact, dense, bright objects separated by enormous distances. The nearest star system beyond the Sun, Alpha Centauri, is about 4.37 light-years away, roughly 41 trillion kilometers or 25 trillion miles. Between stars, there is not a dense hot medium filling the gaps. There is sparse gas, dust, magnetic fields, radiation, and a lot of emptiness. And over the largest scales, expansion keeps pushing the universe toward lower average radiation temperatures. As the universe expands, light gets stretched to longer wavelengths and lower energies. That is why the cosmic microwave background, which came from a much hotter early universe, is now measured at about 2.725 Kelvin. Expansion is not adding cold as if cold were a substance. It is reducing energy density over time. So part of why modern space is so cold is simply that the universe has been expanding and cooling for billions of years. Then gravity creates the exceptions. Stars, planets, and galaxies form because gravity pulls matter together into dense regions. Compression, accretion, and in stars, nuclear fusion create hot environments. That is why the sun is hot and the space between stars is not. Gravity can build islands of extreme temperature, but it does not compress most of the vacuum between stars into a glowing plasma sea. So heat in the universe is concentrated in structures, not smeared out evenly everywhere. Even galaxies do not change that basic rule. A galaxy can contain hundreds of billions of stars, and it still consists mostly of vast dark volume between those stars. So a universe full of stars can still be overwhelmingly cold on average. The heat sources are real, but they are localized. The cold background wins in most of the volume because the distances are huge, and the matter in between is far too sparse to equalize temperatures quickly. And the thermal universe has extremes layered on top of that cold baseline. There are places hotter than stellar surfaces, like supernova remnants, accretion environments, and some hot plasma in galaxy clusters. There are also places colder than most people expect, like permanently shadowed regions and very cold interstellar material. So the real question is not why hot things exist, they obviously do. The deeper question is why that heat does not spread out and homogenize everything. The answer is low density, radiative transfer, enormous distance, cosmic expansion, and time. That is why the universe does not equalize on human timescales, or even on many cosmic timescales the way your intuition wants it to. The pathways that would smooth everything out are weak or absent across most of space. Matter is too sparse, stars are too far apart, and expansion keeps lowering the background energy density. So the universe does not behave like a heated room or a pot on a stove. It behaves like a vast, evolving structure where hot and cold can coexist for immense spans of time, because the conditions required to erase that contrast are usually not there. And that sets up the final step, because once you understand that most of the universe stays cold even while stars blaze inside it, the whole script is ready to collapse into one clean answer. So why is space cold if the sun is hot, after everything we have built? So here is the final answer, as cleanly as possible. Space is cold even though the sun is hot because the sun's energy travels mainly as radiation through a near vacuum, and without dense matter to absorb, store, and redistribute that energy, empty space does not heat up the way air or water does. At Earth's distance, a surface facing the sun gets about 1,361 watts of solar power per square meter outside the atmosphere. But that energy does not turn the vacuum itself into a warm medium. It mostly keeps moving until it hits something that can absorb it. And that longer answer changes how you see everything. The sun really is pouring out relentless energy. But the space between the sun and Earth has too little matter for conduction and convection to matter much. So the energy mostly passes through until it strikes a planet, a spacecraft, a suit, a solar panel, dust, or rock. Then that object heats according to what it absorbs and how effectively it can radiate energy away again. That is why one side of a spacecraft can get dangerously hot, while another side, only a short distance away, can become extremely cold. That is also why planets do not all behave the same way under the same sun. Earth stays relatively warm because its atmosphere and oceans absorb, retain, and redistribute energy. The moon swings between extreme heat and extreme cold because it has almost no atmosphere. Mercury bakes in sunlight and freezes in darkness because it cannot hold and spread heat well. Venus traps heat so effectively that its surface stays hot enough to melt lead. Mars gets solar energy, but its thin atmosphere does not buffer temperature strongly enough. Same star, very different thermal systems. And the answer goes even bigger than planets. Beyond local stars, the universe stays mostly cold because space is sparse and the cosmos has been cooling as it expands. The cosmic microwave background is measured at about 2.725 Kelvin today, which means there is a real thermal background to the universe, but it is extremely cold. So the answer exists on several scales at once: solar system scale, planetary climate scale, spacecraft engineering scale, and cosmological scale. The most useful way to lock it in is this: heat depends on the path it takes. Touching hot metal, standing in warm air, and standing in sunlight are not the same experience because the transfer mechanisms are different. Now remove almost all the air, spread the energy source across 93 million miles, and make every object handle its own balance between absorbed and emitted radiation. That is space. The sun is still hot. The radiation is still real, but the vacuum does not behave like a warm room. So the real question was never just why space is cold. The real question was what heat means when the universe is mostly empty. And once you answer that, the contradiction disappears. Space is a radiative environment, not an atmospheric one. Stars blaze, planets respond according to their own thermal systems, spacecraft survive by managing radiation, and the cold between hot objects is not a failure of logic. It is exactly what the laws of physics predict. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.